So, in the previous lecture, we talked about some functions that can be represented easily by power series. Now we'll talk about a general method for getting a power series representation that works for a larger variety of functions. So 1110 is about the Taylor and Maclaurin series. So, first of all, I just want to introduce some notation here. If you wanted to take something like the 100th derivative of a function called like f or something, well, you need some way to write that, right? The trouble is, if you try to write it using the prime notation, which is Lagrange's notation, you'll have f prime 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 prime, and you'll have to keep doing this until you get to 100, right? That's unwieldy. That's a rather cumbersome notation to say the least. So instead of doing that, we're going to just write f parentheses 100 as a subscript. Okay? And this just means the 100th derivative of f. Okay? So therefore, the first derivative that you're used to is f parentheses 1 of x. The second derivative would be f parentheses 2 of x. And just for notational convenience, we'll also define f parentheses 0 of x. This is just the original function f. Okay? Alright, so now that that's out of the way, we can introduce the Taylor series. So, definition. Let f be a function that is differentiable of all orders When I say differentiable of all orders, what I mean is that its first derivative exists, its second derivative exists, its third derivative, its fourth derivative, fifth, sixth, seventh, 1,000th, 1,001st, 1 billion, 1 billionth first, all of those derivatives exist, okay? So differentiable of all orders, and let A be a real number. Okay. The Taylor series of f centered at A. So the Taylor series of f centered at A is the power series it just looks like sum from n equals 0 to infinity of the nth derivative of f evaluated at A divided by n factorial times x minus a raised to the nth power. And for some reason, when a is 0, this has a special name. I don't exactly know why. In that case, it's called the Maclaurin series. So the Maclaurin series of f is the Taylor series of f centered at 0. So you just replace all these a's with zeros. So what you get here is the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0 divided by n factorial times x minus 0 raised to the nth power. Okay. And just a quick reminder, 0 factorial is 1. So that means that this denominator does make sense even when n is 0. Okay. So theorem. If f can be represented as a power series centered at A, then f is equal to its own Taylor series. To its Taylor series centered at A. Okay. So if f can be represented as a power series about A, then it's always just going to be the Taylor series. Now, that's not true for all functions. Not all functions can be represented by power series on... what I'm trying to say is there are some functions that cannot be represented as power series on any interval. Okay? We won't really be concerned with those in this class or the criteria that you need in order to be represented by a power series. I'm just going to mention that the property of being able to be represented as a power series is called being real analytic. So when I say real analytic, what I just mean is that it can be represented as a power series. So for this class, what we're going to do is I'm going to give you a function, and I'm just going to tell you it's real analytic. And then I'm going to ask you for its power series representation. Okay? All right, so let's look at an example. Okay, so we're going to find the Maclaurin series for f of x equals e to the x, and its radius of convergence. Okay, so the Maclaurin series is just the Taylor series centered at 0. So all we need to do is just say it's going to be this. Okay, so what we're going to need here is just the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0 divided by n factorial times x to the nth power. Okay, now everything there is determined except for the nth derivative evaluated at 0. And that's always the hard part of coming up with the Taylor series for a function. You need to figure out what this numerator is going to be. So, the way that you do this is you just look at a few derivatives of the function evaluated at whatever point you're looking at. A, it's always called, in this case it's 0. And see if you can extrapolate a pattern. Alright? So, in our case, this one is a very easy example. So, the 0th derivative of f, well, that's just the original function, which is just e to the x. And the 0th derivative evaluated at 0, that would be e to the 0, which is 1. Okay, now what if we take the first derivative? Well, if we take the first derivative, then this is still e to the x, because the derivative of e to the x is just e to the x. You evaluate that at 0, and once again, you get 1. So the first derivative evaluated at 0 is also 1. Second derivative. Still e to the x, right? And again, you evaluate it at 0, and you get 1. Third derivative. It's still e to the x, you evaluate it at 0, you get 1. Fourth derivative, it's e to the x, you evaluate it at 0, you get 1. Fifth derivative, it's e to the x, you evaluate it at 0, you get 1. You see where this is going? Okay? So the point here is that the nth derivative evaluated at 0 for this particular function is always just going to be 1. Alright? And with that, we have everything we need to construct this Taylor series. Or, well, it is a Taylor series, but in this case it's the Maclaurin series. So we just need to replace that nth derivative at 0 with 1, and then we just have 1 over n factorial times x to the n. And that is our power series representation for e to the x. Okay. Next up, we need to find its radius of convergence. Well, that's just a ratio test problem, right? So if you want to find the radius of convergence, you just have to take the limit as n approaches infinity of the absolute value of an plus 1, which is just going to be x to the n plus 1 divided by n plus 1 factorial, times n factorial divided by x to the n. N factorial divided by n plus 1 factorial is just always 1 over n plus 1. So this just turns into the limit as n approaches infinity of the absolute value of x divided by n plus 1. So now as n approaches infinity, no matter what x is, that's going to be 0. Okay, so for what values of x is that less than 1? All of them, right? All real values of x would make this limit less than 1. So the ratio test guarantees us absolute convergence everywhere. And that means that the radius of convergence is what we call infinity. Okay? And this is always all you need to do. You just need to figure out how to write the nth derivative evaluated at a. And you're going to do that by just looking at a few derivatives, seeing if you can figure out a pattern. You put that in, and then that's your Taylor series. And then you find the radius of convergence, just like we did in previous lectures. Okay? All right, let's let's do a different example. Let's say now we're talking about f of x equals 1 over x and a equals negative 3. So rather than the Maclaurin series, we're going to say the Taylor series. For the function f of x equals 1 over x at a equals, what did we say here, negative 3? Yes, negative 3. And its radius of convergence. Okay. Just want to point out that the Maclaurin series of this particular function does not make a lot of sense because this function isn't it's not even defined at 0, right? So you're not going to be able to get a power series centered at 0 that represents that function, but negative 3 perhaps. Okay, so once again, all we need is just the sum from n equals 0 to infinity of the nth derivative of f evaluated at negative 3 divided by n factorial times x minus negative 3 to the nth power. Okay? And that's just from the definition of the Taylor series when a is negative 3. Okay, so again, everything here is determined except for this nth derivative of f at negative 3. So we just need to figure out what that is. So, let's see here. The 0th derivative of f, well, that's just the original function, which is 1 over x. And since we're about to take its derivative, I'm thinking that it would be easier to write it as x to the negative 1. So we'll just call this x to the negative 1. And we want to take the 0th derivative and evaluate it at negative 3. That's going to give us negative 1/3. So negative 1/3. And that's the 0th derivative evaluated at negative 3. Okay. Then we take the first derivative. That's going to be negative x to the negative 2. Evaluate this at negative 3. So first derivative evaluated at negative 3 ends up being negative 1 over 9. So that's the same as negative 1 over 3 squared. Second derivative. This is going to be 2x to the negative 3. So then the second derivative, evaluated at negative 3, this ends up being negative, well, it's negative 2 over 3 cubed. Okay. And then the third derivative, okay. Third derivative is negative 2 times 3 times x to the negative 4. And third derivative evaluated at negative 3. This just gives us negative 2 times 3 divided by 3 to the 4th power. If you take the fourth derivative, this will be the last one I'll do. The fourth derivative is just going to be 2 times 3 times 4 times x to the negative 5. You evaluate this at negative 3, and you get fourth derivative evaluated at negative 3 equals negative 2 times 3 times 4 divided by 3 to the 5th. Okay? And at this point, hopefully you can see a pattern here well enough that you can predict the next term in this sequence, which is just going to be the 5th derivative evaluated at -3. Take a minute to think about what that is. Pause the video if you need. It's going to end up being -2 times 3 times 4 times 5 divided by 3 to the 6th. 6th derivative evaluated at -3. That's going to be -2 times 3 times 4 times 5 times 6 divided by 3 to the 7th. And so on, right? Okay, so at least we understand the pattern well enough that we can predict the next term. That's not the same thing as being able to write down the sequence, okay? Those are two very different questions. Being able to predict the next term of a sequence and being able to write down a closed form for the sequence. So, the nth derivative evaluated at -3. Well, let's see here. 2 times 3 times 4, we have a name for that. That's called 4 factorial. 2 times 3, that's 3 factorial. 2 times 1, that's 2 factorial. 1 is 1 factorial, and 1 is 0 factorial. Okay? So the numerator is always just going to end up being n factorial. So this is going to be -n factorial divided by something. Okay. Now let's notice that the denominator here is 3 to the 5th, which is the same as 3 to the 4 plus 1. Denominator here is 3 to the 4th, which is 3 to the 3 plus 1. Denominator here is 3 to the 3rd, which is 3 to the 2 plus 1. 3 to the 1 plus 1, 3 to the 0 plus 1. Okay? So the denominator is always just going to end up being 3 to the n plus 1 power. Alright? And now that we've got that, we can write down the Taylor series. So I'm just going to erase this part and leave the definition up. So the Taylor series, well, according to the definition, it's just going to be the sum from n equals 0 to infinity of, let's see here, -n factorial divided by 3 to the n plus 1. Okay. That's the numerator. Divide this by n factorial, so we're going to have an n factorial on the bottom. Then x plus 3 to the nth power. And that's it. This can be cleaned up a little bit. This can be written as negative sum from n equals 0 to infinity of x plus 3 raised to the nth power divided by 3 to the n plus first power. That's the same thing. I'd certainly prefer the latter way of writing it, just because it's a little more aesthetically pleasing. Anyway, that is our Taylor series of 1 over x at -3. Okay, we're also asked for the radius of convergence, so again, that's just the same thing as we've done before. We just need the ratio test. So the limit as n approaches infinity of the absolute value of an plus 1, so that's going to be x plus 1 to the, x plus 3 to the n plus 1 power divided by 3 to the n plus 2. Divide this by an, which is just x plus 3 raised to the n divided by 3 raised to the n plus 1. Anyway, this thing is just going to be the limit as n approaches infinity. Let's see here. We're going to have n plus 1 copies of 3 canceling. And then what we're left with is just 3 on the denominator. And we're going to have n copies of x plus 3 also canceling, so we're just left with x plus 3 on the numerator. And then we need the absolute value of that. So the absolute value of x plus 3 divided by 3, well, that's just the constant with respect to n. So as n approaches infinity, this is just going to end up being 1/3 absolute value of x plus 3. Now, in order for the ratio test to guarantee you absolute convergence, this has to be less than 1. So we have to have that this thing is less than 1. That's equivalent to saying that absolute value of x plus 3 is less than 3, which just means that the radius of convergence is 3. All right? So yes, this was a bit of a harder example just because it was a bit of a tougher function to deal with. The derivative wasn't just the same thing over and over again. Yeah, this is pretty much how it goes. Also, I just want to point out, to take the derivative here, all we did was the power rule over and over and over again, right? When you do that, you're always going to have an n factorial somewhere in there. The numerator, actually. Okay? If there's more going on than just the power rule, then, you know, different things could happen. But if it's just x raised to a power, and you just keep differentiating that over and over and over again, it's going to have a factorial in it. Okay? All right. Let's do another example, of course. So all that's going on here, I just want to point out, the only thing we need to do here is just plug stuff into a formula, but that's not as easy as it sounds, okay? Because finding the nth derivative at a can be quite challenging, okay? Anyway, this one is going to be f of x equals e to the negative 2x, and we're looking for the Maclaurin series, which is the same thing as the Taylor series centered at 0. And so it's the same thing, okay? Again, we're wanting to figure out what this series is going to be. Everything here is determined except for the nth derivative at 0. So that's all we need to figure out. And then we'll be able to write down the Taylor series. So, the 0th derivative of f, well, that's just the original function, which is e to the negative 2x. And when you evaluate that at 0, what you get is just 1. If you take one derivative, what you get here is negative 2 e to the negative 2x by the chain rule. And so the first derivative evaluated at 0, this is negative 2. You take another derivative. Okay. So second derivative, this ends up being 2 squared e to the negative 2x. You evaluate it at 0, and what you get is just 2 squared. Third derivative. Third derivative is just negative 2 to the third e to the negative 2x. Evaluate this at 0, and you get third derivative at 0 equals negative 2 to the third. Fourth derivative. You take the fourth derivative, you get 2 to the fourth e to the negative 2x. Evaluate this at 0, and you get 2 to the fourth. So hopefully you're seeing the pattern at this point. Next term should be negative 2 to the fifth. Term after that is 2 to the sixth. Then we have negative 2 to the seventh, and so on. Okay? So, the nth derivative at 0 well, it's definitely going to have 2 to the n in it, right? It's going to definitely be 2 to the n times something. And we want the sign to keep flipping back and forth between negative and positive. Specifically, when n is even, we want it to be positive. When n is odd, we want it to be negative. That's easy to accomplish. All you have to do is say negative 1 to the n. So, negative 1 to the nth power times 2 to the nth power, and that'll do it. And so, by definition, the Taylor series is just going to be the sum from n equals 0 to infinity of negative 1 to the n, 2 to the n, divided by n factorial, x minus 0 to the n. And that's the Taylor series centered at 0, otherwise known as the Maclaurin series. Again, I don't understand why the Taylor series centered at 0 has a special name, but it does for some reason. Okay, so then if you want its radius of convergence, it's another ratio test. So you take the limit as n approaches infinity of the absolute value of negative 1 to the n plus 1, 2 to the n plus 1, x to the n plus 1, divide this by n plus 1 factorial, then divide that by negative 1 to the n, 2 to the n, x to the n, divided by n factorial. So, this becomes the limit as n approaches infinity of, let's see, negative 1 to the n plus 1 divided by negative 1 to the n is just negative 1. We're taking the absolute value, so it's not really going to matter whether we have negative 1 or not. 2 to the n plus 1 divided by 2 to the n is just 2. So there's going to be a 2 on top. X to the n plus 1 divided by x to the n is just x. And the absolute value is certainly going to matter for x because it could be negative. And then n factorial divided by n plus 1 factorial is just 1 over n plus 1, so we just have an n plus 1 on the bottom here. You take the limit as n approaches infinity, and no matter what n is, or sorry, no matter what x is, that's going to end up being 0. Which, of course, is always less than 1. So the radius of convergence is infinity. Okay. So now, let's do an example where, so you might be thinking at this point, like, if this always works whenever you have a real analytic function, then what the hell was the point of 11.9, in which we did these weird things to figure out power series representations of functions. Can't you just do this every single time? The answer is yes, but sometimes it is more convenient to use other methods to find your power series representation. Okay, so in the following example, I'm going to try to figure out the power series representation of arctangent x, which we did before, right? But now this time I'm strictly going to just use the definition of the Taylor series to figure it out. And in this case, it's going to be the Maclaurin series because it's centered at 0. Okay, here's how it works. So the 0th derivative is just the original function, and that's just arctangent x. You evaluate this at 0, and you get arctangent of 0, which is 0. Okay, looks good so far. You take one derivative. The derivative of arctangent x is 1 over x squared plus 1. 1 over x squared plus 1. Evaluate this at 0, and you just get 1. You take another derivative. So the second derivative is just going to be negative 1 over x squared plus 1 squared, and then multiply by 2x by the chain rule. So what we get here is negative 2x divided by x squared plus 1 squared. Right? Yes, okay. You evaluate this at 0. What you'll get is 0. Okay, third derivative. We're certainly going to need more, right? Because I can't tell what the pattern is just by looking at these first 3. Maybe you can, but I can't. So we're going to need more derivatives. All right, well, if you want the derivative of this thing, you have to use the quotient rule, which I went ahead and did. It turns out to be 6x squared minus 2. So 6x squared minus 2 divided by x squared plus 1 cubed. You evaluate this at 0. So third derivative evaluated at 0. This turns out to be negative 2. Then fourth derivative, that's another quotient rule, which again I went ahead and did before I started the lecture. So 24x times 1 minus x squared divided by x squared plus 1 to the 4th. Evaluate this at 0 and you get 0. The fifth derivative is going to be 120 x to the 4th minus 240 x squared plus 24 divided by x squared plus 1 to the 5th. You evaluate that at 0 and you just get 24. And you'll have to keep going, right? Unless you see the pattern already, you're gonna have to keep going until you can figure it out. Okay? This one is quite hard. So for this one, I'm just going to erase the definition here because we've dealt with it enough that hopefully it sticks in your mind at this point. If not, then of course you can back up the video, take notes, whatever. So, can we at least agree that the nth derivative evaluated at 0, the nth derivative evaluated at 0, if n is even, that's always going to be 0, right? Okay? So definitely it's always 0 if n is even. If n is not even, though, if it's odd, then it's not going to be 0. Let's see. When it's 1, it's 1. When it's 3, it's -2. When it's 5, it's 24. So, it may not be easy to see, but it's going to turn out like this. So this is if n is even. If n is odd, it's going to end up being -1 to the n minus 1 over 2 multiplied by n minus 1 factorial. This is if n is odd. Right, so now this tells us enough to construct the Taylor series. So here's how we'll do it. This is going to be the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0 divided by n factorial times x to the nth power. Okay, now, can we agree that this series is going to be the sum of all the terms with even n and the sum of all the terms with odd n? Hopefully. So what I'm saying is, I'm going to take this series, I'm just going to take the terms that have n being odd. Well, okay, we'll say the terms with n being even first. Then add to that the terms where n is odd. Okay, well, when n is even, the nth derivative at 0 is always 0, right? So this just vanishes. It just becomes sum of zeros. This one, on the other hand, well, this one becomes the sum from n equals 0 to infinity of -1 to the n minus 1 over 2 times n minus 1 factorial divided by n factorial times x to the n, and this is specifically when n is odd. If n is not odd, then don't do that. Okay? And I just want to point out n minus 1 factorial divided by n factorial is just 1 over n. Okay? So if we desire, we can simplify this a bit by just getting rid of this n minus 1 factorial and getting rid of the factorial on the bottom, and then we just have n on the bottom. Okay, now, let's understand that n is odd. What does that mean? Well, that means that it is an integer. First of all, it has to be an integer in order to be called odd. And it has to be equal to 2 times an integer plus 1. That's the only way that it would fail to be divisible by 2. Okay? So there has to exist some integer out there, let's call it k, such that n is equal to 2k plus 1. So for example, if n is 5, then k is 2. If n is 15, then k is 7. And you can do this for any odd number, right? You can always find this k value. All right. So then in that case, this can be rewritten as the sum from k equals 0 to infinity of, okay, n minus 1 over 2, that's the same as k. So this is negative 1 to the kth power divided by n, and that's the same as 2k plus 1. And then x to the nth power, that's x to the 2k plus 1. And that's our power series representation for the arctangent of x. This is the same result as what we got in the other lecture, right? I think the last lecture, 11.9. It's the same power series representation, but as you can see, this method is a bit harder. Okay? So, yes, the Taylor and Maclaurin series, you can use this method to come up with any power series representation as long as it exists, but it might not always be the most convenient choice. All right? Anyway, they asked us for the radius of convergence. So the radius of convergence here in order to get that, of course, we're doing the ratio test. So the limit as k approaches infinity of, let's see here, absolute value of negative 1 to the k plus 1 times x to the 2k plus 3, because when you replace the k with a k plus 1, the 2 distributes, you get 2k plus 2 plus 1. Well, 2 plus 1 is 3. Divide this by 2k plus 3. Divide this by negative 1 to the k, x to the k, 2k plus 1, divided by 2k plus 1. Anyway, what you end up with here is the limit as k approaches infinity of, let's see here, 2k plus 1 divided by 2k plus 3. X to the 2k plus 3 divided by x to the 2k plus 1 just ends up being x squared. And strictly speaking, yes, we should have absolute values around that, but x squared is never negative, so that's never a problem. Anyway, as k approaches infinity, this just approaches x squared. In order for the ratio test to guarantee convergence, we need that x squared is less than 1, which is the same as saying that the absolute value of x is less than 1, and so the radius of convergence is 1. Which is the same radius of convergence that we found in the previous lecture, right? Okay. So, next up, we've got arctangent of x squared. So, arctangent of x squared at a equals 0. Okay. Now, you can do the whole thing again, right? You can just go through all the derivatives and do the Taylor series directly from its definition again. You don't have to, though. Okay? We already know that the arctangent of x is the sum from n equals 0 to infinity of negative 1 to the n divided by 2n plus 1 x to the 2n plus 1. I wrote it with k's before, but it doesn't make a difference, right? It's just a name for the index. So then if you want the arctangent of x squared, you just replace the x with an x squared. So arctangent of x squared, this ends up being the sum from n equals 0 to infinity of negative 1 to the n divided by 2n plus 1 x squared to the 2n plus 1. And then if you multiply the exponents, you can write that more succinctly as the sum from n equals 0 to infinity of negative 1 to the n divided by 2n plus 1 times x to the 4n plus 2. And that is our power series representation for the arctangent of x squared. Okay. I won't go through the radius of convergence because it's pretty much exactly the same. It will also end up being absolute value of x has to be less than 1. And so then radius of convergence is 1. Okay? All right, and then finally, let's do a particularly important one. Important, but also difficult. So this is the sine of x. I'm going to try to find a power series representation for this centered at 0. Okay, well, 0th derivative is just the original, which is sine of x. You evaluate this at 0, you get sine of 0, and that's 0. You take one derivative, you get cosine of x. Evaluate that at 0, and you get 1. Second derivative is negative sine of x. You evaluate this at, this should be first derivative evaluated at 0, actually. And this is the second derivative evaluated at 0. Negative sine x, which is 0. Or negative sine of 0, which is 0. Third derivative is going to be negative cosine x. Evaluate this at 0. You get negative 1. Fourth derivative is going to be sine x. Evaluate this at 0, and you get 0. And suddenly you realize that this is all there is, right? Okay? You keep taking derivatives, and you're just going to keep cycling through these. All right? So the sequence of f nth derivative evaluated at 0 is going to look like 0, 1, 0, negative 1, 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 and so on. Okay? Okay, so great. We understand the sequence well enough to predict its next term. But again, that is not the same thing as being able to write it down. The nth derivative evaluated at 0. Well, if n is even, we're wanting to say that it's just 0, right? If n is odd, then it's either going to be 1 or negative 1. But which one? Well, let's see. When n is 1, we want it to be positive. When n is 3, we want it to be negative. When n is 5, we want it to be positive. When n is 7, we want it to be negative. When n is 9, we want it to be positive. When n is 11, we want it to be negative, and so on, right? Okay, let's think about that for a second. So the ones that we want to be negative, those are like 3 and 7 and 11, 15, 19, 23, and so on. these are all 1 less than a multiple of 4. Okay, 3 is 1 less than 4. 7 is 1 less than 8. 11 is 1 less than 12. 15 is 1 less than 16. 19 is 1 less than 20. 23 is 1 less than 24, and so on. Okay, the other ones are, well, let's see here. 1, 5, what's the next? 9. Then 13, then 17, then 21, and so on. Okay? These ones that we want to get positive 1 for, those are 1 more than a multiple of 4. Okay? All right, so what we want here is if n is odd, well, then it's definitely 2k plus 1 for some appropriate k. But then it comes down to whether that k is even or odd. Okay? You see, if we say n equals 2k plus 1, that's just the same as saying n is odd. But now if k is even, that would make it 2 times an integer, let's call it L. In which case, this would end up being 2 times 2L plus 1. This becomes 4L plus 1. In other words, it's 1 more than a multiple of 4. On the other hand, if k is 2L plus 1, so if k is odd, then we're looking at n equals 2 times 2L plus 1 plus 1. This becomes 4L plus 2 plus 1, which is 4L plus 3. In other words, it's 3 more than a multiple of 4, which is the same as being 1 less than a multiple of 4. Okay? So what we're saying here is that we want to look at not whether n is even or odd, but whether k is even or odd. Okay? So in order to solve for k, we just have to say, well, if n equals 2k plus 1, then n minus 1 over 2 is k. And so this just becomes negative 1 to the n minus 1 over 2. And by the way, this is the same reasoning that got us negative 1 to the n minus 1 over 2 in the power series representation of arctangent as well. Okay. So now with that, again, only the odd terms will matter, right? So the sum from n equals 0 to infinity of nth derivative of f at 0 divided by n factorial, x to the nth power, we're only going to care about the odd terms. So n equals 0 to infinity of nth derivative at 0 divided by n factorial, x to the n, where n is odd. And again, if n is odd, then this is just negative 1 to the n minus 1 over 2, so let's just replace that. So negative 1 to the n minus 1 over 2. And then once again, as long as you declare that n equals 2k plus 1, this can be rewritten as the sum from k equals 0 to infinity of negative 1 to the k divided by 2k plus 1 factorial, x to the 2k plus 1. And that is our power series representation for sine x. Okay. As for the radius of convergence, let's see here. We take the limit as k approaches infinity of the absolute value of negative 1 to the k plus 1, x to the 2k plus 3, divided by 2k plus 3 factorial, then divide by negative 1 to the k, x to the 2k plus 1, divided by 2k plus 1 factorial. This ends up being the limit as k approaches infinity of x squared divided by 2k plus 3 times 2k plus 2. As k approaches infinity, this approaches 0, no matter what x is. And so the radius of convergence is infinity. And that's amazing. That's amazing because that means that for all real values of x, the sine of x is always equal to this power series. Okay? Who knew that you could figure out a trigonometric function as just a power series? And these coefficients, they're not even that weird. They're just negative 1 flipping back and forth and then a factorial on the bottom. They're integers. So yes, this is it. Okay? Now, as you can see here, having to do this every single time you want to figure out a power series representation for sine of x could be pretty daunting. Okay, so it would be helpful if you could memorize a few power series representations of some common functions. I have a few power series representations of some common functions in an appendix at the end of my lecture notes, as well as some other abbreviated stuff about infinite series. So yes, please refer to that if you get a chance. Homework is up. Go ahead and get some practice with that.